Advertising.
You have like a round fiddle term there.
We're recording now, so just in case.
I have no shame in throwing shade on computer science majors on record. At CU Hackett 2025, when everybody was lined up for lunch, there was a scent. And I was like, this is this is reprehensible. So
This is your homework for me. So next, this homework this week, I think is going to be very computational. So let me tell you what my expectations are. I do not expect you to take these things and row reduce them by hand. For the love of God, please don't do that. But what I do expect you to do is get the answers. You can use algebra systems. Just tell me what you use, right? And for when I ask you to do things like get canonical forms, I'm going to show you that process. Anything that you have to do sort of computationally by hand, you can use Wolfram Alpha, Maple, whatever it is that you like. Just tell me what you used, and this is what I got, and this is how I interpret the output, right? Kind of thing. So in part one, I give you two matrices, the 4x4 and the 5x5. I want you to find for me the rational canonical form, the primary rational canonical form, and the Jordan canonical form if possible. The first two will always be possible. The Jordan, sometimes yes, sometimes no, and we'll discuss that for the matrices over the rational numbers. Number two, let A be a 5 by 5 nilpotent matrix over a field. Nilpotent is important here to show that every eigenvalue is 0. Actually, that's an if and only if. So that is to say a matrix is nilpotent. Do y'all remember what it means to be nilpotent? You just take a high enough powered matrix and get 0 matrix. A matrix is nilpotent if and only if every eigenvalue is 0. Find all the possibilities for the Jordan canonical form of matrix A. And number 3, this is kind of another application of decomposition of a linear transformation, which is kind of cool. Consider the group GL3F2. So these are 3 by 3 invertible matrices over the field of 2 elements. This group has 7 times 6 times 4, so it's got 168 elements in it. This group is simple, right? So if you forget about the abelian groups that are simple, they're all silly. They're all of prime order. This is the second smallest finite simple group, with the smallest one being A5. The second smallest non-abelian one. Find a representative. You all remember the class equation, right? The conjugacy classes. Find a representative for each conjugacy class. This canonical forms of matrices, super handy in doing this, right? And actually, there's not a great deal of, there's 168 elements, but there's not a lot of conjugacy classes. Okay, any questions? All right, let's see here. Oh. Let's see. Okay. So the last thing we talked about was we talked about a way to turn E is n-dimensional vector space over K. And we discussed the way to turn this into a AX module. So E is, well, left, because I'm multiplying left. F of X operating on the element E in the vector space. Well, this E to E, a linear transformation. And we use this linear transformation to get this module action. So this is basically what you get when you plug in phi into the polynomial, so you get powers of phi times various scalars, and have this icon here. And this is in fact, gives a module structure. A K subspace F and E F in E is said to be invariant. And here, invariant is with respect to phi, if phi of F is contained in F. And this is equivalent to the statement that F is a K of X submodule. That F is a KX submodule of E. Because if phi of F is in F, then this persists for every power, right? Phi of F is in phi of F, which is in F, and so forth and so on, right? And so if you look at the way the action works, if phi of F is in F, and since any power, then that means that it takes every element. If E is actually in this subspace F, then this thing is still in there. So it's equivalent to saying that this is a KX submodule. Also, I'm going to give you another definition. Given some V and E, given V, some vector in E, the subspace spanned by the set PIV right? And in fact, I kind of cheated here to make this. I mean, if I want to be for V to be in a phi invariant subspace, then phi of V better be in there, and phi of V, and phi of V, and so forth. And so basically, this is sort of the smallest phi invariant subspace that contains the vector V. And this space is called a phi cyclic subspace. Which is often written E V phi, is called a phi cyclic subspace. And I think the cyclic nomenclature is kind of obvious why they call it that, I suppose. Okay, so I am going to write down this theorem, and this is basically, again, our theorem about modules over PID. Theorem 13.2.3. So I'm going to kind of gloss over some of the details of this because a lot of it is kind of repetition, and then I'm going to show you how to compute things. Suppose we have a linear transformation of a finite dimensional vector space. Let phi from E to E be a finite dimensional vector space, be a linear transformation. Of E, a finite dimensional vector space. Over K. So they're monic polynomials and phi cyclic subspaces. One. there exist monic polynomials. Q1 dividing Q2 dividing QT in KX. And these cyclic subspaces which I will call E1, E2 up to ET, such that E is the direct sum of these phi cyclic subspaces. So I can decompose E into this direct sum of phi cyclic subspaces, E1 up to ET. And each QIT is the minimal polynomial of phi restricted to EI from EI. By the way, let me point out, because these are phi cyclic subspaces, when I restrict down to EI and I input anything into phi, then because of the fact it's a phi cyclic subspace, it's phi invariant. So this goes from EI to EI, right? Yes.
Should that QI parentheses T instead be a QI parentheses X? Because you use T for the
Oh, yeah.
final.
I don't know why I put that T in there. The sequence Q1 up to QT is right. Also, QTX is minimal polynomial of phi. That's the one, that's sort of in a certain sense, QT is the largest one, is minimal polynomial T. And sequence Q1, Q2, QT is uniquely determined by phi and E. There are also monic irreducible polynomials. So here are two. Two, there exists monic irreducible polynomials Q1, Q2 to QS. I call the other ones Q. I'm sorry. I have them called these P's. Yeah, because you're supposed to be here. So they're monic irreducible polynomials P1 through P S and phi cyclic subspaces. What is that kind of mess? Phi cyclic subspaces Vij. I'll double index these. For one between I and S. So the first index, the I index goes between 1 and S for each polynomials. And for each I between J and Ki, and for each I and J between 1 and Ki, which is another integer, we have E is isomorphic to some S Ki J equals names this turn around. K to S E Bij. For all I, there exists integers controlled by I, mi1 up to mik. mi1 greater than or equal to mi2. Greater than or equal to case I greater than 0. No, such that Pi Mij is the minimal polynomial of phi restricted to Vij from Vij again to Vij. Once again, Vij's are all assumed to be cyclic subspaces, so it goes to itself. The P sub i's, M sub ij's are uniquely determined. I need to think about a way of cleaning this second one up a little bit, but basically what we're doing here, this probably looks at least a little bit familiar. KX is a PID, right? This is basically what we're talking about here is the invariant factor decomposition. Because what we have is we have a finitely generated module over KX. And so we've got this module, or we've got this invariant factor decomposition. And this is the elementary divisor decomposition. So this basically is immediate because of the fact that KX is principal ideal domain. It's the same thing that we broke up here. Instead of Z, we just got some of the principal ideal domain. And so the irreducible, the prime elements of Z, and the prime powers, et cetera, are replaced by the appropriate polynomials that are irreducible. So now here's where I have to apologize even more than usual, because I am going to write these canonical forms in a certain way, but the proof I'm going to have to use the transpose. So, and I'll explain that when I get this. So, any questions so far before I put up the decomposition? Yes.
Why do you have to use the transpose for the proof?
because it was the way I was raised. I'll tell you. I'll tell you. I mean, it's basically my own traditions. And the way I'm used to seeing the matrices written. Well, so I'll explain it to you this way. When you multiply a matrix by a vector, do you do matrix times vector? Or do you do vector times matrix?
Matrix type.
Right, that's what I usually do. These canonical forms, however, are written for vector times matrix for whatever reason. Everything I always saw was that way. So you would have to transpose mine to get the usual way when I write these canonical forms. So I'll go ahead and write that down. I'll give you some explanation when we get there. Theorem 13.2.4. Suppose that phi is a linear transformation from a finite dimensional vector space to itself. The linear transformation of E, a finite dimensional vector space over K. Then V is phi cyclic with minimal polynomial. Is phi cyclic with minimal polynomial. Q equal XDR and of course I can take my monic polynomial, or I can take my minimal polynomial and be monic, which I will so choose here. If and only if the dimension of E is R, and there exists a basis for E relative to which the matrix of phi is given by zero, one, zero, 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 zero. Where's zero here? Zero, 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 one, zero, 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 one, and right. And here, just kind of help you along. Okay, so this is called rational canonical form. And there are a couple of ways you can do this. You can use the rational canonical form in terms of invariant factors or elementary divisors. And I will give you examples where we can see all of this. But this is called, notice this block is fairly easy to work with. I think we could all agree, right? Because it zeros everywhere. You got ones down the super diagonal, and then these elements across the bottom are essentially the minimal polynomial, direction, reverse, sign change, right? Here's, let me show you why this works and why I'm reversed. Okay, it's phi cyclic with minimal polynomial, this. What this means is phi to the r v is equal to minus a0 I. Well, let me just take the v out. Minus a1 phi minus a2 phi squared minus ar minus 1. Everybody agree with that? Just manipulating the minimal polynomial, right? This means that this thing, if you have phi rv, it can be written as a linear combination of the lower ones, right? So any phi rv can be written as a linear combination of this. And this is why this works. Let me show you kind of what happens here. You write this down. 0, 1, 0, 0, 0. Two, three. This is why this works. So put the basis in terms of V and what it's cycled from. So the first basis element is V. Now, what happens? What happens when I do this matrix multiplication here? I get 0, 1, 0, 0. Right? Everybody agree with that? When I do the matrix multiplication this way, this row times this column gives me a 0. This row second column gives me a 1, right? This is phi of V, which is the second basis element, right? I agree with that. This one now I get 0, 0, 1, 0, 0, 0. So see what this matrix is doing is it's shifting this V squared. It's shifting this one to this one, which is one of the first entry, one of the second entry, one in the third entry, and so forth. Everybody agree with that? That's why this matrix works. And what happens to the last one? So the last one, I guess that's a good question here. What happens when I have 0, 0, 0, 0, 1? Well, now all the zeros are up. I don't get any contribution from this except from the bottom row. I get minus a0, minus a1, minus a2, minus ar minus 1. Agreed? And my translation of this is minus a0 times v minus a1 phi of v minus a2 phi squared of v in terms of this basis minus ar minus 1 phi r minus 1 v, which by this is phi rv, which is exactly where it's supposed to be, right? It should just be the next power of this. Am I okay with that? So hopefully trying to do that answers your question, because if I wanted to do the multiplication on the other side, I would have to transpose this matrix. Right, and I'm just used to doing it. I like the ones on the super diagonal because I'm a silly man, and that's all there is to it. Right. Okay, any questions on that? Yes.
So are these just the standard, vector, or what, like, where are we getting these from?
Well, so what this thing says is if V is phi cyclic with minimal polynomial, blah, 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 there exists a basis. And my basis is basically V. I'm gonna take V to be, it's like a change of basis thing. V is 1, 0, 0, 0. And V of V is 0, 1, 0. It's where this is pushed and so forth.
Oh, okay, so it's what your input, like phi of E is what you're multiplying by.
Right.
Okay.
Because what you're doing every time is you're hitting this with phi.
Mhm.
Right? So when you hit this with phi, it kicks it here, and finally it kicks it back to phi to the
Okay.
And this is what this matrix is allowing us to do, right? Go from phi to phi of v, and basically this matrix tells you to kick it to phi of v, which is the next basis element, and the next basis element, and so forth. Everybody understand how it's working? Yes.
But he, like, if you do phi r times on anything in V, don't you get the zero matrix?
No, you'll just start over again, right?
Oh.
So now you've got this linear combination. Now you can do it again and then apply the identities and,
Right.
right? So when you do it again, you'll have this, and now you'll have a phi r and you'll have to feed that back in. And, computationally it becomes kind of a big mess, but it works out pretty good. Okay, I'm gonna give you one more special case that can happen, and then I'm gonna show you how to do this. How to actually compute these matrices. And by the way, this is just for one phi cyclic subspace. What happens if you have several, which is, what you would expect to encounter in the real world? And the answer is simple. You just glue the pieces together. Every phi cyclic subspace is a piece of the matrix. And again, I will clarify that in just a moment. Corollary 1325. Here, again, we have the same situation, phi from ED, a linear transformation. Linear transformation, finite dimensional, vector space, E over K. Then V is phi cyclic. With minimal polynomial, x minus lambda dr. If and only if the dimension of V is R, and relative to some basis, phi as matrix given by this lambda 1 0 0 0 0 0 lambda 1 0 0 0 0 0 lambda 0 0 0 0 lambda 1 0 0 0 lambda. And again, transpose. So this matrix has, this is in the particular case where you've got a minimal polynomial that looks like this, right? In this case, you can sacrifice that bottom row being just a string of things. Now this one is upper triangular, And it's actually really, I mean, it's almost diagonal, right? It's got well, actually, more than that, it's almost scalar. It's got lambdas down the diagonal, but it's got ones on the super diagonal. Right. Now, notice that the rational canonical form is more general because it just takes on the polynomial and you basically have to use the coefficients for the bottom row. In a certain sense, this is better because it's upper triangular. But you can't always do this because you may not always be able to take your minimal polynomial for the matrix and break it down into perfect powers, right? For example, if you have the polynomial x squared plus 1 and you're over the rational numbers or you're over the real numbers even, you cannot write that in this form, right? Because you can't, you need I and minus I to be able to break it as a linear to a power. Now, if you're over the complex numbers, you're good to go. Because x squared plus 1 is x minus I times x plus I. And so you have an x minus I to 1 power. So that would be a block. And an x plus I to 1 power, and that would be another. What do I mean by blocks? Well, let's just kind of, I can't resist this one. Proof. This is a corollary, and I can't resist it because I think this is kind of cool. Let pitchfork, pitchfork minus phi. Be lambda I. Go this way. Then Q is that right? Right. Then this is the minimal polynomial for phi. Well, this is minimal polynomial for phi. If and only if x to the r is minimal polynomial for pitchfork. Right? So basically, so I want this to be, oh, right. So that means that if this is the minimal polynomial for phi, then x to the r is the minimal polynomial for pitchfork. So the matrix just use the rational canonical form. What would the matrix look like? Well, the minimal polynomial is x to the r, right? That means I've got zeros all across the bottom here. That's the matrix for this. And phi is pitchfork plus lambda I. So now just add the lambda I here and you get the canonical form that we have here. Okay, let me show you how to do this. And my first example, I think, is important, but it might feel like a little bit of a cheat. So we'll fix that up. Example. So here's an example.
Dr. Quinn,
Mhm.
I'm sorry, but when we have in the rational canonical form there, right there you have dimension of E is equal to R. Is that V instead or no? Because we're only dealing with one.
Oh, V and E are synonymous.
Oh,
Where did I use it the most? E. Let's suppose. That I have a linear transformation over Q with invariant factors. X squared plus one. Suppose I have phi. From E to E. Over Q. With invariant factors. Let's call it F1. X squared. X squared plus one squared, x two squared. Well, I guess I'm gonna write the bullet here. This is x4 plus 2x squared plus 1. X squared minus 4x plus 4. Which is x6 minus 4x5. X4, I get a 4. And a 2 is 6. X cubed, I get a minus 8. X squared, I get 8. X, I get minus 4. What's that? Okay, and I get 1, oh no, 2 more, x equals 1, x minus 2. And this equals to x cubed minus 2x squared plus x minus 2 and x squared plus 1. You better check me on that, make sure that I'm good. Looks like I'm good. Find the rational, find canonical points. By the way, this last one is called a Jordan block. And this goes with the Jordan canonical form.
In the canonical form, so V is always that, like that's always good. Or V is defined as like 1, 0, 0.
Yeah, oh, you can define it, right? I did the change. V is just V, it's some abstract thing.
Oh,
But I can make the basis depend on V, right? So I can use that to build the basis. Okay, so let's look at. So just think of breaking up QX, or generally KX, and these modules. So these are the invariant factors, okay? This allows me to give what I call the Jordan, rational canonical. And it's pretty easy to build. By the way, can somebody tell me what the dimension of my vector space here is? 7. Where did you say it?
it's X to the 6, so 6 plus 1, 7.
That's 11. Subspace dimension 6, 3 is the top. So basically if you take, and by the way, the carrot, I don't know what this matrix is. In fact, this is just a linear transformation. But any matrix that you make for it, the characteristic polynomial of that should be the product of those 3. So it should be this 11-degree polynomial that's the product of these 3. That's what the characteristic polynomial. But so basically, here's what happens. you have these phi cyclic subspaces, one of dimension 6, one of dimension 3, one of dimension 2. And every one of these gives you a block in the rational canonical form. I'll go big to small. The 6th block is 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0. I am not, by the way, going to write all 121 elements, these only the ones I care about. 0, 0, 0, 0, 1. And let's see, what do we get? Minus 4, 4, minus 9, 8. Minus 6, 4. There's your first block that corresponds to that first invariant factor. Agree? Next invariant factor, next block down the diagonal. By the way, the order you put the blocks in doesn't matter. It's all the same up to conjugating by some matrix. The next one's a 3 by 3. And that should be 2 minus 1, 2. And finally, I have just a humble little 2 block here. And let's see, that was x squared plus 1, so that's minus 1. The other entries that I haven't filled in are all zeros. So this complicated 11 by 11, 121. I mean, look, what do we got here? 5 and 6 is 11, 12, 13, 16, 17, 18. Right? I've got 18 non-zero entries in a matrix with 121. So this will be much more easier to handle than this. You can also do what's called a primary rational canonical form. And primary is to the regular as doing an elementary divisor decomposition is to doing invariant factors. So we have to figure out here, what are the elementary divisors? So I'm working backwards here. Anybody know what they are? So they should be the prime powers. Actually, the first way I've got this written is probably perhaps easier. Would everybody agree that x squared plus 1 is a prime over q? Right? This can't be broken down any further, right? X squared plus 1 is irreducible in qx, and therefore it must be prime. Because irreducible is a prime in a principal ideal domain. So my elementary divisors are x squared plus 1 squared, x squared plus 1, and x squared plus 1. It's actually repeated 3 times here. And let me note that this one is x4 plus 2x squared plus 1. That's the only thing I've got to multiply out. And 2, my other ones are x minus 2 squared and x minus 2. And again, this is x squared minus 4x plus 4. 2, 3, 7, 8, 9, 10, 11. Okay, again, I'm just kind of gut checking to make sure that puts together to be 11 by 11. Now you make the blocks you make the blocks the same way, but instead of using the full invariant factor, you now just use these prime powers that we've kind of harvested from that mess. So this is called the primary rational canonical form. Okay, again, I'll take this apart piece by piece. The first block is going to be a block of 4. And it's going to be minus 1, 0, minus 2, 0. So there's the block corresponding to that. There should be another 2x2 block for this. This one is 0, and an identical one down here. Now I take apart this, this gives me a 2 block. -4, 4. And finally, this gives me a 1 block, which is just lonely little 2 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Everything else that I haven't put in there, they're all zeros. So this is the primary rational canonical. Now, this matrix does not have a Jordan canonical form over the rationals or the reals. And the reason is you cannot break all your irreducibles down into linear polynomials. Right? That's the problem here. So for next time, we'll figure this out. So see if you can tell me what the Jordan canonical form of this is if you're over the complex numbers. Okay, any questions on that? Any questions? Okay. Well, let me remind you